All right, so continuing on with class 17, I'm going to do three quick examples. I didn't do these in class because I wanted to try to maximize our time moving on to the drag and then lift in class 18. But these will just possibly, I said it possibly, I would skip these. I said right there in the thing. But these are from Munson, and they're really, the benefit of them is just to quantify some things right here. So we have an example where we have this small 15 millimeter fish. He's pretty small, like a minnow. And he spins at 20 millimeters per second, which I guess is pretty good for a 15 millimeter fish, sure. And we want to find out if the boundary layer type of flow will be developed along the sides of the fish. And this is explained. Really, the thing that we're looking at is trying to recall that the boundary layer type flow occurs when we're at a Reynolds number of about approximately 1,000. Right, so we want to try to find the Reynolds number here. So the Reynolds number that we're going to use, the X one. No, we're not using the X one. We're just going to use the length. I'm sorry. So this is just based on the length of the thing. If I go back to my notes, it wasn't based on the X. We're going to go and use U for the velocity L, and then use nu instead of mu, right? We're remembering that this is the kinematic viscosity, which is the dynamic viscosity divided by the density. So it's just a sort of a shortcut to make it just ever so slightly easier. And so we're going to say that this is in fresh water. And so the velocity, let's make it in meters per second. So what's that? 0.02 meters per second. And then the length of this is 0.015. Is that right? No, I think it's supposed to be 0.2. I think that's supposed to be 0.2. Sorry. No. I think I got it right. Boy. All right. And yeah, so this is going to be meters. Okay. And then if you take a look at for fresh water, the kinematic viscosity, you find out that you get at regular conditions 1.12 E minus 6, and you'll see that it's a meter squared per second is the standard units for those, and we end up getting 267.9, right? So that's going to be smaller than 1,000, and therefore not a boundary layer. Not a boundary layer flow problem. So we wouldn't be worried about the development of a thickness and being concerned about what happens within that thickness in order to do this. Okay, so here we have another problem. We have water that flows past a flat plate that is oriented parallel, right? So we're going this way right here. It's a flat plate. And the flow upstream is going to be 0.5, so that's big U, 0.5 meters per second. And we want to determine the proximate location along this leading edge, where the location from the leading edge, where the boundary thickness becomes turbulent, right? And so they were showing it like it was growing, right? So, what is the boundary layer thickness in this zone? So we kind of want to find this place right here. And so we want to find the location, call it X, from here, where we are going to make that transition. And we're going to use Blasius. And I added, what is the shear stress going to be at that location? And we're going to say that that the RE, I guess critical is the 500,000 mark, right? So that's what we're using as going to be the laminar to turbulent. Because previously we said it was sort of a range of things, but we're going to settle on 500,000 as being our location here. So we will set our RE X of, okay, so we'll go U. It'll call this XCR because it's going to be critical, and new right here, and set it to 500,000. So we can find our XCR by moving the thing around and going 500,000 times, we're going to use water again, so we had used it right up above, so 1.12 e to the minus, let's say, 6, right? And if you wanted to, we could include the units right in there. So that's going to be meters squared per second. And divide that by also, yeah, we're going to divide it by the speed, right? So that's going to be at 0.5 meters per second, because that's what we said up here. And we find an XCR, I'm not leaving myself a lot of space. It's going to be quite small. No, actually, it's going to be pretty large. It's going to be a pretty good distance, 1.12 meters. That's not insignificant. So if we're going to use velocius along with that, remember that the velocity is first we said that we could get the thickness by saying 5 times the square root of nu x over u. They might have had an L in there. So 5 times the square root of the 1.12 e minus 6 and the x of 1.12 meters, and then of a 0.5 meters per second, I guess. I don't know why I just used units right there. So we end up finding a thickness at that location at 1.12 meters along up here is going to be 7.92 e minus 3 meters, which is approximately 8 millimeters, right? So you can see how that, you can kind of get an idea how thin that it's going to be. And then we can also say, that's the boundary layer thickness. Then we can also see what the shear stress is going to be along there. And Blasius says that it's going to be 0.332 times the velocity raised, the far field velocity raised to the 3/2 times the square root of, now we need the density times mu, right, times divided by x, right? So we didn't write down all of these values, but we can get them. 332, we have the 0.5 to the 3/2. Let's see if we can squeeze all this in. We're going to get 999 kilograms per cubic meter, and we'll say that this ends up being 1.12 e to the minus 3, 1.12 e minus 3 for the dynamic viscosity, all divided by our 1.12 meters. So we get the shear of being 0.117 newtons per meter squared, right? So that's a pretty small amount of shear, considering, maybe we'll think that atmospheric pressure is 101,000 newtons per meter squared, right? So this is not a lot of shear stress, but we're just trying to quantify it here. And then lastly, we have the boundary layer on the hood of your car. Behaves like a flat plate. We want to estimate how far from the front edge of the hood the boundary layer becomes turbulent, right? So how far, and then how thick is that going to be at that location, right? So here's one. I'm going to use U.S. or British gravitational units for this. So I'm still going to use the critical length of 500,000 right here, and so RE critical is the 500,000. I'm going to estimate that I'm going to go 65 miles an hour. Not me, no way. I'd go much faster than that. 93.33 feet per second. It's going to be ironic if I die in a fire rate crash. That's pretty dark right there. Sorry. Anyway, I have the dynamic viscosity 3.74 E minus 7. Of course, this is going to be air, right? I'm not going to drive in the water, not on purpose at least. and that's pounds second per square foot. We'll get the density in case we need it of 2.38 E minus 3, and these are slugs per cubic foot. And so we get to get the nu instead of the mu for the kinematic viscosity, 1.57 E to the minus 4 square feet per second. Right. So start out right here. Remember, we're going to write down this equation for as a function of the Reynolds number is a function of position. It's going to be u times x divided by nu. So we could figure out what the x is going to be equal to by taking the 500,000 and multiplying by the kinematic viscosity, 1.57 E minus 4, and dividing by the speed, 95.33. And I guess I could fit that right into there. Well, let me put it right below. I don't want to crush over here. So we end up finding that we're going to have 0.8235 feet, which is going to be, maybe I'll write that CR is going to be 9.88 inches. So not very far from the front of the hood. And we could find our Blossius. And I'm not going to plug in the numbers. We're just going to find out what it is. But this is what we'd use, right? We'd have to get the thickness of this. It ends up being 0.0699 inches. And then if we wanted it the wall shear, and that's only up at that location, right? That's not across the entire hood. So we're just looking at there, right in there in the laminar region only, right where it makes that transition. And that again, by the way, that's the 0.332 times u to the 3/2 times the square root of, where's the formula up above? We already wrote it up here, right? Rho u, big capital U. No, that's mu. Sorry, mu divided by x, right? We stick all those numbers into there, and we get 0.1208 pounds per square foot, and we could multiply that by 144, and we could see what we get for PSI, right? Am I saying that correctly? No, we would divide by 144, wouldn't we? Yes, we'd have to divide by 144, so no real point in doing that. It's not going to give us anything that's going to be of any interest to us, so we'll do it anyway. 8.39 E to the minus 4 PSI, right? Not a whole lot of shear, but we're talking about a very limited, a limited problem here, right? We can only deal with the Blossius solution, can only really get us for laminar flow. And so we're just talking about that transition spot between where it's going from laminar to turbulent. That's what we're trying to find. And we're quantifying that's what the shear stress is going to be right there at that point, right? You can see the shear force per area at that location. So we are done.